In this video, we'll start Chapter 5, which discusses discrete probability distributions. This is in contrast to Chapter 6, which discusses continuous probability distributions that we'll talk about next. I encourage you to take a moment to go and look up the definitions of discrete and continuous from Chapter 1 to get a feel for how we will approach these concepts differently. The first thing that we're going to work on is constructing a probability distribution for a random variable. We're going to find the mean, variance, standard deviation, and expected value. Now for many of these terms, mean, variance, standard deviation, you already know what these are. Expected value is going to be a new one. Then we're going to talk about the binomial experiment and the binomial distribution a bit. We're going to find the probability of exactly X successes and N trials. Then we'll find the mean, variance, standard deviation, and expected value of the binomial. You'll enjoy this part. It's going to be nice and simple. In this video, we're just going to talk about this first piece, looking at the probability distribution. So let's get going. So first of all, recall that a random variable has values that are determined by chance. There's an element of chance that's going to be involved with what value that random variable takes on. Also, we've got discrete and continuous, as we mentioned before. Discrete means it has a finite number of values. Think about the number of students in a classroom. These can be really big numbers, like the number of raindrops that hit the ceiling in a thunderstorm. But think that even if they're really big numbers, we can't have half a student or we can't have half a raindrop. If two raindrops split, then two raindrops hit the ceiling, and we have two, but we don't have 32.5 students in a class. We don't have 3.5 million raindrops that hit a ceiling. In this, we're specifically going to be looking at discrete variables for this chapter, and consider why as you're going through. Maybe take a moment here and there to think about how this would be much tougher if we used continuous variables instead of discrete. Now the first element is going to be to relook at our experiments and to rephrase these problems. So in these experiments, typically we've been looking at the sample space and the event space, and we've been comparing and contrasting these to calculate probabilities. But now what we're going to do is we're going to take the same situation, 3 coins that are being flipped. This was a classic situation. I know you're bored of it, but 3 coins that are being flipped, and we're going to relook at this as a different random variable. We're going to look at this as if X, the number of heads, is our random variable. So we're going to tend to call our random variables X, but what we're defining that as is the number of heads. Now thinking about this using a bit of common sense, we can see that the number of heads is either going to be 0 if it's all tails, 1 if there's just 1 heads that was flipped, 2 if there's 2 heads that were flipped, and so on, and that these are all of our possible options. So the first step in looking at these probability distributions, these discrete probability distributions, is to rephrase into a term that we call random variables. So we can make up a whole ton of these. We'll try an example later on. So we have X assuming these different values. Now, as part of creating a probability distribution for these discrete values, and to remind yourself these are discrete, we can have 0, 1, 2, or 3 heads. There's a finite number of options. We can't have half a heads. We can't have a quarter of a heads in 3 coin flips. We've only got 0, 1, 2, or 3. So this is a discrete case. But to make a probability distribution, we need the probabilities. So now what we're going to do is we're going to look at all 4 of these values for that random variable, and we're going to calculate the probabilities. Now you can use the frequency over the sample space. That's an option. But remember, this frequency, this is the number of elements in our event space. Looking at this in a different way, we'll see if I can use technology here. We can look at this as the probability of X is going to be the number of events in our event space, number of outcomes in our event space, and divided by the number of outcomes in our sample space. This is what we had when we were doing this earlier. This is typically how we looked at that equation. So looking at the probability of X equals 0, we can write this out by hand, the probability for X being 0. Well, if we want to look at the event space of X equals 0, the event space is just going to have one way for 0 heads to happen. So if you think about 0 heads happening, we've just got one way for that to be. That's going to be tails, tails, tails. So the size of our event space, this N of E, is going to be 1. There's only one way that can happen. And earlier we looked at the sample space. So this sample space guy is our, what we wrote out in that previous slide. There's going to be 8 elements in that sample space. And remember that you had the fundamental counting rule where you look at each of the K's and you can multiply those together. So K1, we have 2 options for the first coin flip, 2 options for the second coin flip, and 2 options for the third coin flip. This gives us the size of the sample space, 2 times 2 times 2 being 8. Now it might be a good second to go on and pause your screen. See if you can go on and calculate the probability of X being 1, 2, 3. All right, so we've got the 1 out of 8. Checking your work, X equals 1. We've got tails, tails, heads, tails, heads, tails, or heads, tails, tails. We've got 3 out of 8. Note that you don't have to show all this work here. You just have to be able to give me enough so that I know where you're coming from. So you don't have to write out the full event space for each of these. Probability of X equals 2 is 3 out of 8. Probability of X equals 3 is 1 out of 8. Typically, when we're using these discrete probability distributions, we're going to summarize into a table that looks like this. So this is going to be how you're going to see this in the future. X, whatever your random variable is, written out as 0, 1, 2, 3, and then the probabilities written out down below. Now X can be any random variable, so right now take a moment to consider, what if we had a different, maybe a weirder random variable? I'm going to use X as the number of heads times the number of tails. What if we had that as our random variable? What would that look like? So right now, go on and pause your screen and see if you can put together a probability distribution of the form X and then each of the probabilities of X for this random variable. See what you got. Coming back to this, you can watch it worked out here. When we have X, for each one of my values, I want to look at the number of heads and number of tails. Now the sample space has all of my different values in it. Tails, 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 heads, and so on. Now if I look at all tails, I'm going to have 0 heads. The number of heads is going to be 0. The number of tails is going to be 3, and I'm supposed to multiply these. This would give me a value, not of 3, that's silly, of 0 for this particular response. If I have 2 tails and 1 heads, I'm going to have 1 times 2, and this is going to equal 2. And again, looking at my equation, 2 tails, so I put in 2 for the number of tails. 1 heads, so I put in 1 for the number of heads. I get 1 times 2, and that's what gives me 2. Doing this out for the rest of my sample space, I find that the only 2 values that X can take on, that is the only 2 answers in this row, the only 2 options I have are 0 and 2. There are 2 out of 8 ways for me to get the response of X equals 0, and there are 6 out of 8 ways for me to get the response of X equals 2. These discrete probability distributions, as you're noticing, are determined by theory. We call this classical probability. We can display these as a table as we've been doing, but we could also use a formula or a graph, and actually in a couple slides we'll look at an example with a graph. To see these for some common cases, remember to not overthink these. If you're rolling a die, the probability that you get a 4 on a die is 1 out of 6. So this is a really simple, straightforward discrete probability distribution. Discrete because there's a finite number of X values. We can write them all out. And it's a probability distribution because we have the probabilities of all those X values. Now if we flipped, this should say 4 coins, excuse me, but if we flipped 4 coins, this would be our probabilities of each one, and we can draw this as a graph. Note that because these are discrete values, this is going to not be a histogram, but our bar plot. Notice the spaces in between each of these values. This is something that we didn't talk about in Chapter 2, but the heights are going to be the probabilities. So this is like a relative frequency bar plot. In fact, you can look at the probabilities of each of these as your relative frequencies. Now we can also set this out just as we have before, looking at a World Series. The number of games in a World Series is, the World Series are best of 7, so the series lengths are between 4 and 7 always. Now in 40 World Series, these are the number of times each of these occurred, and our goal is to find the probability distribution for X. Now it's important to note first, what is X? Here, X is the number of games played in the series, so this is the series length. This is what our X value is. This is what we're interested in. Now, randomly, we'll have a game that falls into one of these categories. So how long a series is a random value. We don't know it ahead of time. It's determined at least somewhat by chance, probably determined by many chances. So what I'm going to do is eventually I'm going to write my x's across and my probability of x's across. My x values are going to be 4, 5, 6, and 7. Now I just have to find the probability from these occurrences. You can think of the occurrences like frequencies. This is the same as in Chapter 2 when we found relative frequency. Or we can solve this the empirical way. So remember, an empirical probability, that's the number of observations divided by the total number of trials. So in this case, we had 40 trial games. 8 of them were observed to have a series length of 4. 8 divided by 40 gives us 0.2. Solving this out for the rest of these, we see that our different probabilities, 0.175, 0.225, 0.400, and now we can combine these in fraction or decimal format into the probability distribution. So this is the discrete probability distribution of the series length X. Just like before, we can still graph these. Note that there is an order down here. We talked about how in bar charts there are typically no orders, but there is kind of an order. The series length is going up. We just have to keep the spaces in here because we aren't allowing anything to be in between 4 and 5. You only have an option of 4 and 5. 4.5 isn't an option. So our traditional histogram is not going to look appropriate for this data situation. Now, when we're identifying requirements for a probability distribution, there are 3 requirements. First, the variable must be numeric. So for a discrete probability distribution, the variable needs to be numeric and have values that can be associated with probabilities. Otherwise, we can't very well have a probability distribution. Next, just as we talked about in Chapter 4 when we talked about probabilities, the sum of all these events in the sample space must be 1, so all of our probabilities should add up to 1. That is, we should be looking at all of the probabilities of X when we're writing out a discrete probability distribution. Finally, these probabilities have to be formal probabilities. That is, each of the probabilities needs to be between 0 and 1, and it can be 0, that's the little equal sign below here. It can be 0, it can be 1, but each one has to be between 0 and 1. So let's try some examples. Feel free to give these a shot on your own. These are some pre-made discrete probability distributions. So in this distribution, we can look, we can see, check through our checklist of is this a discrete probability distribution. So first we check if the values are numeric. We see that they are. See if the values sum to 1. And in this case, if I added all of these values up, they all have the same denominator, so I just add across the top. Negative 6 plus 2 plus 17 plus 7 plus 15 does not equal 1. Are the values between 0 and 1? No, they're not. This value right here is negative 6 out of 10. That's below 0. This value right here, 15 out of 10, is above 0. Thus, this is not considered a probability distribution or a discrete probability distribution. Looking at this case, we investigate. The values are numeric. The values sum to 1. The values are all between 0 and 1. So this is to be considered a discrete probability distribution. For one more case, the values are numeric. The values sum to 1. And again, if you want to check this, type all these in on your calculator. 2 divided by 3 plus 1 divided by 6 plus 1 divided by 6. It's not a bad way to check. Or if you can do some mental arithmetic, that works well too. All the values are between 0 and 1, so this is a probability distribution. Note that these don't have to be fractions. These can be decimals too, so we can look. All the x values are numeric. The values do not sum to 1, and again, if you add all these up on your calculator, you're not going to get the answer 1. And the values are not all between 0 and 1, so this is not considered a probability distribution. This video has been our introduction to probability distributions. The next video, we'll talk about the mean, variance, standard deviation, and expectation of these distributions.